We have seen many quizzes on Canvas coming in, and let's get started. Jibran, Rashid, basics of a quantum program. The floor is yours, and we look forward to the new fire on Discord to Jibran's questions. Thank you.
Thank you very much, Marlo. Hello, everyone. Welcome to day 2 of our QWorld workshop within our larger workshop. So I'll start off answering quickly a question that was on Discord regarding a clarification about the application of the CNOT gate. So the idea was, well, what does the CNOT gate do? What is its structure? We agreed on the definition of what the CNOT matrix looks like. That was this. And then one way to figure out, well, what the CNOT matrix will do, or the gate will do, is to just apply that matrix to kind of the 4 basis vectors that you can have. And you can imagine it's just the standard basis vectors, right? And so in a 4-dimensional space, so you could just write down the 4 basis vectors as what you would imagine from your linear algebra class. And then the idea is, for a purpose of computation, if you know the effect of any gate, not necessarily just the CNOT gate, on these 4 vectors, then you would know what the operation is on any arbitrary vector, because for our purpose, any arbitrary vector would be a probabilistic combination of these 4 vectors, right? So you just take the probabilistic combination of the application of CNOT onto this. So for our purpose, let's imagine that we labeled this as E00, E01, E10, E11. So that would mean that to begin with, let's figure out what CNOT applied to E00 will give us. So C0 is the C0 matrix. E00 is kind of this first standard basis vector. What's the vector that I should get out over here? Right? So I've got an E rather than a C, but yeah, E00 comes back again. And we mentioned this yesterday, as you can note that we've got essentially, not erase, highlight. We've got the identity over here on kind of 00 and 01. And so that's what one would expect. You get E00 out over here as well. Now, what if we were doing the application on E01? The same idea, we get E01 back out again. If you were to apply it on E10, though, we note you can do the full matrix vector multiplication, or just kind of note that, hey, wait a minute, in this case, it's kind of the NOT gate that's being applied. You do the matrix vector multiplication as well to verify that in this case, the output vector will be E11. And then for E11, the output gate will be E10. So one thing would be to just do this computation, plug and chug, and you've got the answers out. Then you want to step back and say, well, can I kind of logically understand what the effect of this gate has been? And the idea that you say is, all right, in this situation, you want to treat the value of the first bit as what we call the control bit. And the second bit in this case is the target bit. And the idea is when the control bit is 1, i.e. in these 2 cases, then the target bit flips its value, right? And so that's the net effect of the CNOT gate. And the idea is this kind of verification of what any given gate does is kind of a nice quick check. You take kind of the matrix representation, you take its effect on the standard basis vectors, and you've got essentially a complete factorization of what that gate is doing on the inputs. All right. Then we had this question, and I'll still kind of leave it open in terms of what the solution is. There were a couple of responses already on Discord yesterday. I don't think there were many other responses today, but it's kind of a question that's out there. So you feel free to post your solutions on Discord, or just figure it out on your own. And we move then to finally today, what we're going to talk about, basics of a quantum program. More actually in terms of what the basics of quantum information or quantum computation is. As I mentioned, the perspective of these sessions will be coming in from the computer science perspective. We're abstracting away from physical details, physical realizations, actually, even though they are of the utmost importance. And so the idea is, from a computer scientist perspective, we'll take the key fundamental tenets of what is needed from quantum physics for the purpose of quantum computing. And so today, what you'll hear a lot of times being thrown around is this notion that you don't necessarily need quantum physics background or physics background in order to do quantum computing. That's definitely true. But as also kind of mentioned in the talk just before, to really kind of make progress in the field, you do need this interdisciplinary perspective. You need people from different fields working together. So if you wanted to make progress, even in just terms of coming up with a new quantum algorithm, it really does help not necessarily to just have the standard vanilla flavor introduction to quantum computing. The more quantum physics you know, the more tools you have in your toolbox to figure out how to develop a new kind of quantum algorithm, or how to think about a new quantum algorithm. With that said, we'll kind of think of our current discussion as now the quantum generalization of our formulation yesterday, right? So we started yesterday with notation and terminology for perfect classical bits. deterministic bit, what would be perfect transformations, deterministic transformations on that bit, then move to lack of knowledge or information, and hence the introduction to probabilistic bits and transformations on those probabilistic bits in terms of stochastic operations. And now we generalize it even further to the quantum realm, and then we say, hey, all right, what is going to be a quantum bit or a qubit? What doesn't change from our formulation yesterday is that we are thinking of modeling a quantum device. Let's still call it X, why not? Its state set, sigma, for the purpose of this talk, is still going to be just this 0, 1. So a quantum state, a quantum device, the device that we are modeling via quantum physics or via a quantum computer, we still imagine it to have only 2 physical states, and we label them as 0, 1. Then the central claim of quantum physics that gets applied for our purpose is the following. And many of you might be already aware of this, right? To describe an isolated quantum system, we need to give an amplitude. And what is an amplitude? Well, in the general case, it's a complex number. For each possible state, we can find the system to be in when we measure it. So again, we are not necessarily taking the full kind of postulates of quantum mechanics derivation of quantum physics. We are kind of just taking the key tools that we need. And the first key tool that we need is, all right, if I want to describe a quantum bit, what I'll need, rather than what we had in a probabilistic bit, i.e. we had a probability component, rather now I'll need this notion of an amplitude, which in general would be a complex number. Given that I'm looking now at a quantum device with 2 states, naturally there will be 2 complex numbers for it. And now we can contrast it with the classical versus the quantum. So classically, what we've already seen, so classically we had this vector v, which we wrote as p, let's say 1, 0 plus 1 minus p, 0, 1, and see we got this vector p, 1 minus p. Quantum mechanics tells us that if I want to represent 2-state physical device, what I'll have is alpha 1, 0 plus, let's say, beta 0, 1, and alpha and beta are complex numbers in general, but naturally there will be some kind of restrictions on alpha and beta. They will not be arbitrary complex numbers, because then we'll run into kind of issues in terms of how are they related to reality. Kind of a small quick disclaimer, in every program that you will write in QBronze, in the Jupyter notebooks, we assume for the sake of simplicity that these amplitudes are real numbers for, when you're writing your programs. I'll just use this notion of these amplitudes being complex for these first 2 slides. And then for the purpose of our QBronze workshop, I restrict myself to this limited notion of these amplitudes being real numbers. It's only a restriction for the purpose of presentation of the material in slightly simpler fashion. So all the operations would be over real numbers rather than over complex numbers. And then when we move over to the silver workshop, which will discuss Shor's algorithm, which does quantum Fourier transform and hence needs complex numbers, we'll start working with complex numbers again, right? So for the purpose of just the next 2 slides, we'll use complex numbers. And then for all the remaining discussion in QBronze, we'll assume these numbers, these amplitudes are real. So as Aviral has already mentioned on Discord, the restriction on these numbers will be something of the form alpha magnitude square plus beta magnitude square equals 1. Where exactly is this coming from? Well, we somehow are linking ourselves to how are these amplitude notions and whatever these amplitude represent. We'll have more to talk about that today later. For the moment, let's just see how from these amplitudes we get to something that's already more familiar, i.e. probabilities. And for that, we've got something known as the Born rule. That's the second thing that we take as a given from our toolbox of quantum physics. And that kind of says that probability to see a particular or to observe a particular outcome. Example, probability that X is in state 0 is given by absolute value square of amplitude. So that's the key segment. So first thing is this notion of representation now is in terms of complex numbers that are thought of as these things called amplitudes. And then how are these amplitudes connected to probabilities that we are familiar with? Well, this is this mathematical rule that we will be applying. What does that mean? That means if I've got alpha as my amplitude, then the probability to see the corresponding event or to see my physical system in the corresponding state is given by alpha magnitude square, which you might recall if alpha is equal to a plus ib, which will then just be a square plus b squared. You can just write a square plus b. If alpha was just a real number, you could just say alpha square and be done. For complex numbers, that's this thing. Now, whatever I'll mention kind of then follows from, right? So if this is our connection of how amplitudes are linked to probabilities, and there is kind of interesting research in terms of refinements of Born rule itself as well, then the normalization constraint from probability theory ends up implying the notion that for an arbitrary qubit, quantum bit or a qubit is given by, now we'll have the restrictions, v equal to alpha 1 0 plus beta 0 1. Alpha beta are complex numbers. And now we could say alpha square plus beta square equals 1. Why? Because we have this notion that alpha magnitude square is a probability. And then the only two events that we have, the only two states in our sample space, state being state 0 and state 1. So normalization then implies that alpha magnitude square plus beta magnitude square should be equal to 1 to give us normalization of probabilities. Any questions here so far? Right, so that's kind of the basic introductions. We've already, using these two kind of fundamental ideas from quantum physics, have our representation of how we depict, how we formulate a quantum bit in quantum information. Naturally, what's not at all obvious is how to think about what these amplitudes really represent physically. We'll talk more about that soon. What if we restricted these amplitudes to be real numbers? As I mentioned, naturally, the discussion becomes simpler, restricting amplitudes to real numbers. And Bill Wouters has indeed a nice paper on, in fact, defining something that he calls a rebit, and based on a rebit, then deriving how much of the standard quantum physics you can derive from it. And the idea is then you just have a parameterization of a qubit using the standard parameterization, and you'll have cosine square theta plus sine square theta equals 1. So the key distinction from classical information to quantum information is that instead of a probabilistic combination, we have what is termed in the literature a superposition. Right? What do we mean? We are saying cosine theta 0 plus sine theta 1. And the obvious question to then ask is, because that would complete the entire, that's the range for theta in order to get our entire range for normalization. Right? The question that pretty much every quantum physicist would have their own perspective on, what is the physical reality of this state? Don't take kind of the key extreme points where you've just got 0 state and you've just got 1 state, but let's assume you've got some interesting values of theta. So you've got something that is a combination of both the state 0 and state 1. When you took the classical state, you had this nice interpretation. Imagine if you're doing a coin flip, right? You really have this interpretation of a coin flip as operational interpretation where you could say, all right, I would flip this coin. And if I were to repeat this multiple number of times, the number of times or the ratio that I would get of number of heads versus the number of tails would be given by this p and 1 minus p. So that's your link to reality. What's the corresponding link to reality for these amplitudes? It's a more kind of interesting discussion, and which we'll get to. Because, so you essentially are going, so it might be a closed interval, right? So you are essentially going from, if you can go just from 0 to 1, you've got the entire thing. Any questions other than the range issue with theta? If this is then our definition of what a representation of quantum information would look like, the standard next thing we would want to do is, what are the operations that we can apply on this standard bit, quantum bit, to evolve it over time, just like we did for classical information. So what do you think would be the key feature that we'd like to impose on the set of transformations that would transform quantum states over time? And if you already know the answer on what that restriction is, kind of step back and think about more in terms of just what we know about these quantum states. Don't just give us the final answer. So sine theta and cosine theta are just being used as a way to parameterize these amplitudes if these amplitudes are representing real numbers. It gives us a nice way to parameterize. And we'll come more into visualization of this soon. So you can imagine a visualization of a qubit as essentially just a vector on kind of a unit circle. We'll come to different parameterizations for sure. Just stay tuned for that in upcoming sessions. But for the moment, if we fix this as our parameterization, and now ask, well, what kind of transformations would be allowed on such states? How would you imagine coming up with kind of a logical reason for coming up with it? So what I'm thinking of is in this form. We want all operations that map quantum states to quantum states, right? We should not be mapping out of something that's not a quantum state. So that's one way to approach thinking about, well, what kind of operations should be allowed or can be allowed. So if I have something that's a quantum state, whatever I map to after applying my transformation should still be a quantum state. So I imagine my transformation, which would be a matrix of some form, let's say because we're in the finite case. And I imagine my vector representing the different states I can be in of amplitudes. It will map to another vector, which will still have a bunch of amplitudes, let's say given by beta sub I, and would still have the requirement, right, that alpha sub I and beta sub I are real numbers given our restriction. And now what would be the requirement for this vector to be a quantum state? That we just already know is this. Then for the transformation to be a valid transformation, this thing has to be also a valid quantum state. And so I get that this thing has to equal this as well. And so what you're getting is something that you could say is U transpose U equals identity. U is reversible. In general, if you were looking at the complex case as well, that it has to be unitary. The interesting thing is that if you think of this as reversible, then what we are essentially saying is that there is no information lost in applying these transformations. And that goes back to an earlier definition of a qubit in terms of thinking of this as an isolated quantum system, right? So there's no information leaking into the environment. So all that we are modeling right now using the state representation of vectors is for perfect quantum transformation with no leakage, with no noise or more interesting physical concerns taken into consideration. Why is the input vector so long? Because I'm trying to think of it in general terms. Naturally, you can just think of it as a single qubit as well. But the idea here is that this operation could be thought of as being applied to an arbitrary quantum state. And so when we're thinking about what kind of transformations would be applied, would be valid for a quantum state, the restriction that we are coming up with is this. Another way to think of this is that the norm is being preserved, or the L2 norm or Euclidean norm is being preserved. So let's look at an example of such a transformation. We've already seen some classical transformations that are valid examples of quantum transformations, but let's look at something uniquely quantum. Could everyone quickly just verify that this transformation satisfies the property that I had for our transformation to be a valid quantum transformation? Information is reversible before measurement. No, it's not the information. The point is that the transformation is reversible. So the idea is an inverse of the transformation exists. You can apply that to get back your original state vector. Yes, for physicists, it's your time evolution operator. One example then of such an operator is on the screen, which all of you might already be familiar with in terms of being called Hadamard. And let's try to see what it does to our standard qubit. So moving forward, this is a nice time to introduce standard quantum notation, which is your Ket notation. And we say that we use this label, we define it to represent the vector 1, 0, and we do this representation, define it to represent this vector, right? There is no necessity to use Ket notation, but it is really useful in some quantum computations. Computation scientists who really don't like to use this notation and use standard linear algebra vector notation, that's perfectly fine as well. It's basically whatever you are comfortable with using, but it's again something that you'll see used in the literature quite often. So it's important to be familiar with it. Right, so for the moment, for the purpose of our discussion in QBronze, we are discarding considerations of the complex part in the amplitude. We are assuming the restricted formulation where the coefficients, the amplitudes are real. We will have opportunity to talk about the whole kind of picture when we start off with our Q-Silver discussion, where we'll have complex representation for the amplitudes. And we'll see that just me restricting ourselves to real amplitudes still gives us lots of interesting things to say about the stuff. Right, so naturally, since we are restricting it, it still satisfies the property of what it means for it to be unitary, but we are not necessarily including all unitary transformations then. So think of this as just standard vector, linear, and matrix multiplication. So you've got the unitary matrix representing an evolution over time. You've essentially kind of done the entire integration to get your each individual time steps to, rather than just say, if I go from T0 to T1, then that entire evolution is captured by applying this unitary U, right? So what is the effect of this matrix H on the state 0? You would write it like this, but now using our Ket notation, we may also just kind of write it like this. What would be the output? In Ket notation, preferably. So there are still some questions about H, whether H is unitary or not. Just compute H transpose H. It's plus state. What is the plus state? Well, we can verify that this will look something like this, which we then label as the plus state as well. Similarly, H applied to 0, 1, which is just H applied to the 1 state, will give me something that looks like this. The key difference is this minus sign, and hence sometimes generally people will write it as this minus state. Okay. Now, what we want to compare and contrast this with is what we saw yesterday in terms of a classical coin flip. We saw that the matrix representation for a classical coin flip was just half all ones. And you could think of it as f applied to 1, 0 equals f applied to 0, 1 equals just this half 1, 1. And it's kind of a similar idea as being obtained over here as well. If you go back to our bond rule description, then what we are saying is that if I apply Hadamard to the 0 state, if I apply Hadamard to the 1 state, the state that I'm getting out, if I measure it, if I look at it, in both cases, I find probability half to see state 0, and I find probability half to see the state 1. So just in that discussion, I don't get much new out from comparison to the classical coin flip, but that's slightly deceiving because the minus sign does indeed come into play, and that's what we'll see next. To begin with, and just kind of what we've presented right now is if I am just thinking of a coin flip, a single coin flip, then there doesn't seem to be much difference between me flipping a classical coin, which is represented by this F, versus a quantum coin flip, which is represented by this H. I would get the state plus or minus out, given whether or not initially my coin was in the head or tail state, 0, 1 state. I flip it and I get a quantum state vector out, such that when I measure it, the bond rule essentially says, all right, I get probability half 0, probability half 1. That's exactly what classical coin flips give me as well, right? So what's the difference? So let's discuss classical versus quantum coin flips. I'll just rewrite what we already kind of know. If I started in state 0, and now I did a classical coin flip, but now I do 2 coin flips in sequence versus I start in the state 1, and then I do my classical coin flip, and then I again do my classical coin flip. So let's think of this kind of as a quantum circuit or a classical circuit, where I'm saying I'm starting over here on the left-hand side, and then evolution is happening as I move towards the right, and what's happening is I'm performing classical coin flips. All right. Now, what I want to compare this is, we haven't done kind of the discussion of it, but what I want to compare this now is this quantum situation where I imagine I could start in the 0 state, apply Hadamard, and then take whatever comes out of it and apply Hadamard to it again. Similar thing could be done with the 1 state, Hadamard, and go here, versus a slightly different experiment, a quantum experiment, where I again start in the state 0, have a Hadamard, but then in between the application of these 2 Hadamards, I have a measurement. So this notion over this symbol over here represents a measurement. And when we're thinking measurement over here, just think of the bond rule statement that we just discussed, and then we'll apply Hadamard again. And same thing for this case. All right. So the classical part is easy. Let's quickly work through that. I did a classical coin flip. I started in, let's say, the head state, which I represent by 0. I applied a classical coin flip. I know from my previous discussion and earlier discussion, and from all the times I flipped a coin, that I will get half times head and half times tail. Now, there is no kind of real notion of measuring classical coin per se, right? So you just look at it, you know the result, that's it. Even if you don't see the result and you flip the coin again, it doesn't really change the statistics of what you produce over here at the end, right? So what would you say are the statistics that you will observe over here at the end in this classical experiment over here? Right, so I'm looking for what's the output over here. What are the statistics I would see over here? So I'll just see this half 1, 1 vector out over here, and everyone will agree I'll see this half 1, 1 vector over here as well. And this statistic will not change regardless of whether I stopped in between over here and chose to look at what was the measurement, what was the result of the first coin flip over here. So over here, the coin flip over here could have resulted in a head or a tail. Doesn't matter. Regardless of that result, I perform the coin flip again, and the result is still kind of a perfect coin flip out. Now, if I take the standard quantum version of this experiment, where Hadamard now represents my quantum coin flip, you can verify that this half 1, 1, 1, 1 is not a valid quantum operation, right? So coin flip for the quantum case will be represented by H. And so if I apply H, as we verified in the previous slide, what I'll get over here is the plus state, and what I'll get over here is the minus state. Well, the nice thing that we know about H, the Hadamard operator, is that it's self-inverse. You can verify that the inverse of the H matrix is H itself. And so that tells you something very nice about what you expect as the output over here, right? In the case when you start out with a 0, the output over here will be exactly 0, and we start out with a 1 over here, and the output will be 1 over here, right? So performing two coin flips because of the structure of quantum transformations ended up canceling each other out, and you got exactly what you started out with. Now you repeat exactly that same experiment, but you add a measurement in between, i.e., rather than having this plus state and minus state that is fed into the second Hadamard, you are now performing a measurement. That measurement, given our formulation of thinking about quantum states being projected into a certain state vector with a certain probability, says that when I measure over here, well, with probability half, I will get the state 0, and with probability half, I'll get the state 1. So when I measure over here, because I had applied Hadamard to the state 0, and I measure it with probability half, I'll get state 0. With probability half, I'll get state 1. I had the state 1 over here. I applied Hadamard. Over here, what I've got is the minus state. Yeah, so the state collapsed to exactly one of them, right? So either with probability half, it will be projected into the 0 state. That's one way of thinking about it. And with probability half, it's projected into the state 1. It was the minus state kind of before measurement. Once we perform the measurement, the minus state is projected into post-measurement. This plus state was either 0 or 1. Similarly, the minus state got projected into 0 or 1 with probability half each. Now, when I apply Hadamard again, over here, the state I would get is either the plus state or the minus state, the plus state or the minus state over here. So the statistics I will see at the end over here will actually be exactly half of the time heads and half of the time tails. So I could get the plus state or I could get the minus state, but the statistics of measuring that, if I were to measure them over here, will be that half of the times I get a head, half of the times I get a tail, which is completely qualitatively different and quantitatively different from what I had in this previous quantum experiment. And the only distinction between these two experiments was me kind of performing a measurement in the middle over here. And so I'll let that kind of sink in. Different people have different takes on it. And the key issue, as I mentioned when I labeled this as, or as it is labeled in the literature as superposition, is, well, what exactly is the physical reality of superposition? One way I like to think about it is, imagine if you had a classical coin. The idea is that even if you had perfect knowledge about the coin flip, you knew exactly at what point of the coin did you apply the force, what was the weight distribution of the coin, what was the gravitational distribution, such that you were able to exactly simulate the coin flip, how the coin is rotating as it flies up into the air and lands, then you could actually perfectly predict, whether it will come up heads or tails. And the idea is somehow quantum mechanics is saying we don't have accessible information even about that. What exactly is the physical reality of a physical system when it is in the state plus or when it is in the state minus? It is not correct to think of it like you would think about a coin in a probabilistic combination of half 0 or half 1. And that's what this exercise really pushes through, I think. And the key point for emphasizing that is this philosophical direction that this field takes in terms of quantum interpretations. And people have talked about various different quantum interpretations based on their own kind of understanding and own kind of personal belief system as well. Here's this kind of survey that happened in a quantum conference towards the end, where this was a conference full of quantum physicists, experts in quantum physics, and the organizers basically kind of sent out this survey asking about which interpretation of quantum mechanics, quantum physics do they believe is correct or do they prefer. And you can see there's kind of this nice distribution over all different possibilities. We haven't really talked about Bell states. Note that in this previous example, we just have a single qubit. So we are not talking about any fancy stuff like entanglement. We're really just talking about a single quantum bit. So, and we are kind of identifying something uniquely, innately quantum over here in terms of how to understand the reality of what physical reality of superposition is. And different quantum physicists have different interpretations of how they would like to think about it. One of the pragmatic interpretations I think that has emerged out of quantum information is to basically just take the interpretation that works for you for the current situation, which I kind of also favor. The interesting that you see over here is also how the probabilities over here, the percentages over these bars don't really add up to 100. So there are multiple different favorite interpretations that people had of quantum mechanics as well. But interesting, kind of the nice anecdote over here is that at the end of this conference and survey, Asher Perez, one of the pioneers in our field, kind of gets up and says, and who here believes that the laws of nature are determined by a popular survey? So I think it's an interesting take on multiple different spectrums of how people think and feel about quantum mechanics and interpretations of quantum mechanics, right? So for sure, you can just have this shut up and calculate mentality and perspective, which is fine and works perfectly. But then you also want to, at some point, stop and think about, well, what am I actually modeling? What's the actual physical reality of the stuff that I'm modeling? And then kind of it opens up the field in terms of what interpretation you have. The spectrum of interpretations is all out there, right? From one end to another, and everything you can imagine between as well. For people who are interested, there are nice online lectures on an entire course on interpretations of quantum at Perimeter Institute, if you're interested. And there are many other interpretations as well over here that are not listed on this chart as well. So quickly moving on to multiple qubits. And here I'll kind of emphasize a point that was mentioned and came up in the previous discussion as well. We already kind of know what's happening based on our discussion yesterday, actually. So we already noted that when I have two probability vectors, the way to combine them out is to take a tensor product. And so nothing actually is changing here now. When I have now two quantum bits, so let's say psi is qubit 1, alpha 0 plus beta 1, and I've got phi, which is equal to gamma 0 plus delta 1, then combining them together would be psi tensor phi, and I'll just get the nice big superposition out. I'll have alpha gamma 0 0 plus alpha delta 0 1 plus beta gamma 1 0 plus beta delta 1 1. And you can again think of this as just how we wrote down the tensor product last time. This is alpha gamma component, this is alpha delta component, this is beta gamma component, and this is beta delta. And so note how the indices of what we are writing in the Keck notation actually represent the index of the corresponding coefficient as well, right? So alpha gamma is the amplitude for index 0 0. Alpha delta is the coefficient for index 0 1, and hence the Keck 0 1 as well, and so on and so forth. So that's a nice kind of representation that we have. And once you start getting really large vectors, as you will in quantum information, and they'll be sparse vectors, this representation really just helps. Now, question that came up in that discussion is the notion of simulating quantum systems via classical machines, right? So there were statements of, if I wanted to simulate 30 quantum bits using a classical computer, if I wanted to simulate 20 classical bits using a quantum computer, let's actually first note something simpler. What if I had quantum bits that could be written always as a tensor product? So imagine I have n quantum bits, but in addition, what I know about those n quantum bits is that they are, or they can be written in this tensor product decomposition. What would be the amount of classical memory that I would need to simulate those n quantum bits, if those n quantum bits can be written down as a tensor product decomposition? So what I mean is, if I took my n qubits and the corresponding state, let's write it out as a capital psi, it's written as alpha 1 0 plus beta 1 1. That's qubit 1 tensor, alpha 2 0 plus beta 2 1 tensor, so on and so forth, until I've got my nth qubit, alpha n 0 plus beta n 1, right? So I've got these n qubits. Those n qubits are in this tensor product decomposition. What's the benefit of writing them down in tensor product? So I'm not actually saying that there's a benefit of writing them down in this decomposition of tensor product. I imagine you're talking about this decomposition and not of the earlier combination. I'll come to the combination later, but right now let me just emphasize this point. If these n qubits admit this decomposition, I'm not saying n qubits can always be written in this way. As we already mentioned last time, even two probabilistic classical bits may not be written in a separable way. But here what I'm emphasizing is that these n qubits assume they have this decomposition. Then assuming they have this decomposition, what you note is that for each qubit, I can really actually just keep track of the alpha sub I. The n qubits, and let's not worry about the complex versus real part, because that just again adds an additional constant factor. I'll need to keep track of two real numbers rather than one real number. So for simplicity, let's just talk about real numbers only. Each of these alpha sub i's and beta sub i's are real numbers. And again, a simplification you can do is, because of the normalization constraint, rather than alpha and beta, I just need to remember alpha. Then even though this vector psi is of size 2 to the n, but in order to keep track of all the coefficients in this vector, I only need to remember n numbers. I could just choose to remember alpha 1, alpha 2, alpha 3, all the way up till alpha n. And if I know those numbers, then I can for sure construct this entire 2 to the n size vector from these alpha sub i's only. And so if psi is separable, i.e. has this decomposition that we've mentioned above, then we only need, and here let me use some classical computer science notation, capital O of n, or in other words, linear memory for keeping track of the quantum state, track or storing the quantum state, right? So there's nothing interesting in some sense happening of quantum nature in the sense of a quantum advantage if my state has this decomposition where each n qubit can be written down as its own individual thing, and the joint state vector is the tensor product of everything together. Then what I have is linear memory complexity or space complexity for keeping track of this entire vector. This becomes interesting for the purpose of quantum computation and quantum simulations and writing quantum programs as well. Then what I could do is just keep track of this n O of n memory, apply whatever operations I need to do. I only need to apply an operation to these n elements to figure out how the state will evolve. Hence, if there is anything interesting that will happen on a quantum computer, or there is a quantum algorithm that does exhibit quantum advantage, we know that at some point in its computation, it will not admit this decomposition. Because if it always represents this decomposition, then we know that there's an efficient classical simulation for it. So hopefully the key takeaway point is clear, that quantum states that always have this tensor product decomposition admit a nice, efficient classical simulation. And so if you are going to have something that's going to exhibit quantum advantage, you will need to have situations where these quantum states get entangled with each other. O of n in this case might not be huge in the sense that n is just linear in the amount of memory you have. It's just like saying I have n number of bits, classical bits for my memory. Similarly, you're saying I have n number of qubits for my memory. And so in some sense, the representation is completely analogous to classical bit versus quantum. But when we say that, as kind of has already been mentioned in this code, if these quantum bits do not have this decomposition, then exactly these quantum bits are entangled. They might not all be entangled, but at least some component of them would be entangled. And that's exactly a uniquely quantum feature. And hence, we might expect that because the quantum state is exhibiting this phenomenon of entanglement, it may exhibit or may be usable for some interesting quantum behavior or quantum advantage. So I will upload these slides via Discord as well. I should have done that yesterday already. I didn't. All right, so hopefully the key takeaway point is okay on this end. And so what was being mentioned in the slide in the discussion by Oliver as well, when we are giving these comparisons that 30 quantum bits will require a supercomputer, or it was like 30 bits can be done on laptop, 50 will require a supercomputer, and so on and so forth. What you're really doing is just computing this 2 to the 30, 2 to the 50, and so on and so forth. But this 2 to the 30 is being computed under the assumption that the quantum state that you will keep track of is this arbitrary quantum state that does not have this tensor product decomposition. It could be an arbitrary entangled state, and hence you'll need to keep track of that entire state vector. If you go back and look up the discussion that happened when IBM proposed, Google proposed their quantum advantage, and similarly, different experiment was proposed from China as well. The key idea, especially for the Google experiment, was exactly this, that, hey, if you wanted to simulate this via the IBM supercomputer, then the best classical approach was essentially just to say, initially at least, to take this entire vector and store it in the memory. And this vector was just too large to store in the memory, and hence it was difficult. How we got to know n linear memory is required? Because the idea was that if the state vector has this decomposition given by this tensor product, what I'm asking you to observe is that this tensor product construction, the way I get this large vector, can be computed by just knowing alpha 1, alpha 2, alpha 3, and so on and so forth up till alpha sub n. Just knowing all the alpha sub i's is enough for me to construct this entire vector of size 2 to the n. And that's why linear amount of memory or an amount of memory is sufficient. Questions? So what we'll do today is actually take a break here. We've been conceptually heavy, even though the content was limited. Now I'll take kind of a poll. Would people rather see a small introduction to kind of the Qiskit program today, and then again a smaller discussion tomorrow, or just see a longer discussion tomorrow? Alpha and beta are positive. Yeah, alpha and beta for sure. We've got this normalization constraint on them. And yes, I should have mentioned that they are positive as well, for sure. Yeah. No, the only constraints are that alpha square plus beta square equals 1. Apologies. The constraint on alpha and beta is that alpha square plus beta square equals 1. Let's work more on Qiskit. What we'll do is finish off today. I'll take some questions if there are. And then tomorrow, then we'll start with a longer discussion on the anatomy of a quantum program in Qiskit. We'll do that discussion and finish off a discussion of quantum operations. Okay. All right. So we'll end today with this, and I'll upload the slides right after this discussion. Marlon?
Thank you very much, Jibran. For the homework for QWorld today, what do you recommend based on where you got so far?
So they can definitely start out looking at Qiskit programs. That will make my task easier for the discussion of the Qiskit program tomorrow. Well, first, to begin with, you want to make sure you've looked at the classical program stuff from yesterday, because that leads up to the quantum program formulations. But the quantum program formulation relies heavily on Qiskit. If you look at the introductory notebooks on Qiskit, they are kind of very self-explanatory. They work you through the details of what the notation is. We'll do all of that tomorrow as well in detail. And I'll try to give some background material as well in terms of how to think about the different things that the Qiskit library is doing. The recommendation for people to do today is to at least go over those notebooks. They can treat the Qiskit introductory notebooks as independent from yesterday's work, because today's notebooks are being used for the purpose of introducing the Qiskit library. So I would recommend you definitely do that before our session tomorrow.
Thank you very much. All right. Thank you very much, everyone, for attending the Introduction to Quantum Computing by William Oliver today, the QWorld Basics of a Quantum Program or Quantum System by Jibran today. It means that the homework on Canvas for today is one assignment for quantum computing hardware introduction to quantum computing. Just a few questions about the lecture that William Oliver gave, very short. And then after you finished the homework from yesterday for QWorld, you can continue with the second quiz there about the basics of a quantum program. And there are additionally the Jupyter notebooks to practice. Tomorrow we will have two exciting sessions again. We will start with a session on entrepreneurship, quantum entrepreneurship, and the steps to take in there. And then Jibran will be back with everything he just promised to you. Looking forward to seeing you then. And we just gathered a list of questions that we are relaying to IBM and Keysight. So stay tuned for their lectures on Friday and Tuesday to learn more about control and readout of qubits and about superconducting qubits. Thank you very much all. We will close the session and see you tomorrow.
Thank you.